Sir, in the same way, how that assignment questions in the same level only that final paper will be there more than that. I can expect.
I I guess it should be easier than that. I don't think it should be difficult, more difficult than that.
No, sir, if you should maintain that level, I'm preparing in that level only.
Yeah, I don't think it should be small. It should be tough than that. It should be tougher than that. I think it should be easier than that.
Yeah. Yes, sir. They mean with one problem, there will be multiple questions also. May expect at the final of the exam.
It can be. It can be. I don't know about it. It can be. It can. It may not be. I have no idea about it. This again. This is decided by the instructor, so I have no idea about it.
Mm. Yeah, yes, sir. Up to 6 weeks, one up to first 6 weeks, one term, and later on 6 weeks is other thing also.
No, I don't think it will be done like that. I mean, it should be all the portion will be there in the main exam,
Yes,
right
sir.
from the
I
start.
mean that flow is different, no, sir. That within first 6 weeks is one connection is there after that
Yeah, so
moderate
basically
from.
till no, but the thing is that everything is connected, right? I mean, for the first part of the course, you learned about negative feedback and learned
Hmm.
about the two-stage op amps on a block level description, right? After that, you learned about noise and things like that, and then you started learning about transistor level implementation of the amplifier, isn't it? So all the things are connected. It is not like that is another. This is another part. It's not like that.
Yes, sir. Sir, in sir, Iman Mandal, sir, class high frequency circuits that one miller, 2 miller compensation techniques are there, no, sir. That is equivalent to that what professor taught in this
Yeah,
course,
yeah,
also.
right. It is yes.
Rather than any more anything else.
It is. It is almost same as that. Yes. Alright. So I guess without any further ado, let's start. I'll share my screen.
Sir, in the high frequency circuit, sir, that
Uh-huh.
assignment questions will be available, sir, in our website.
Uh, no, no, it will not be.
It is private, right?
It will not be available.
While going to that, I mean specifically E613A, while
Yeah, yeah, it will
opening,
not be available. No assignment answer solution is available.
uh, at least questions, sir, for practice.
That you can refer to any standard book, isn't it? I already told na. Refer to
Yes, sir,
Ravi's book.
I'm following, sir. Week
Yeah,
11 only, I got 67. Few weeks I got with that book only, sir.
yeah, yeah. So that's all. You practice your questions from there. That should be enough.
Yes, sir, but for week 12, I didn't see the deadline, sir. The deadline is passed. I don't even submit. Can I get a request for a.
You can try, but I don't think it will help. You can try mailing the instructor for this course, but I don't think it will be helping.
Okay. Sir, anything for the preparation, sir? Can you give a flow? How to
Just
start?
uh, just redo or
Right now,
revise
I'm
all
in
the.
a differently, sir. I just completed that multi-stage unfolded cascade.
Yeah, yeah. Just
Partly
revise
is.
all the assignments, all the concepts. You can maybe try solving the questions which I was posting along with the questions that I used to solve. Along with the question that I solved in the class, I also was posting questions for you
Yes,
to
it's in
solve.
the document. Yeah.
Yeah, so you can maybe solve them, try solving them, and it should be fine if you do that. You should be fine.
Okay. Yeah.
Hmm.
Sir, how will
Yeah.
be the difficulty level of the exam? Because this
I
is
guess
the
it
first
should be
time I'm
easier than
preparing
the.
for the
I
course.
should. I guess it should be easier than the assignments that you have practiced.
So will there be like everything in like those like everything we have to calculate, or will there be something like MCQs also, like
That I
simple
have no idea.
MCQs?
That I don't know. I don't know the pattern. That pattern should be, that pattern is not standard. Okay, it depends upon the instructor who's taking the course. So I
Okay.
guess it should be MCQs, but well, I don't know. I cannot say for sure. Yeah. So don't take my word for it. I seriously don't know what is going to be the pattern. Okay.
Okay.
Yeah. When is the exam, by the way?
Coming Saturday,
Okay.
29.
Fine. Just revise everything and you should be fine. I don't think you should have any problem. Okay.
Yes. Yes.
Yeah. So okay, let's start. So this is 1 second. It's recording fine. Yeah. So this course is analog IC design, and it is taken by the instructor Dr. Shankaran Aniruddhan. He is a professor in the Department of Electrical Engineering at IIT Madras. Also, my name is Mayank Karpon. I am the tutor for this course. My I am also a PMR scholar, and right now I'm doing a PhD in electrical engineering at IIT Kanpur. Fine, so this is the introduction. Now, as I promised in the last tutorial, this is supposed to be a. I'm not going to solve anything today. This is going to be devoted to you. So, whatever you ask, I will solve. If you have any doubt, I will clarify that. If nothing, then we can all go home. I'm nothing to cover for today because I already covered everything till this week 12, in the last session itself. So whatever you have, I will discuss. Otherwise, I have nothing else to discuss here. Maybe I will start summarizing, and you can ask me anything if you want to ask. So yeah. So in the
Hello,
last,
sir.
yeah, yes.
Uh, Sir, can you repeat us like how to start
I'm sorry.
designing and uh,
Hello. Excuse me. Your voice is cracking. I guess the internet connection is not very good. Can you please uh, repeat everything which you said, but this time go slowly.
hello, sir.
Yeah, yeah.
Can you hear me?
I'm sorry. I'm not able to hear you. You can maybe type your question in the this thing message.
Okay.
I can see it. Yeah. And so anyway, I was saying that I will simply summarize everything which we summarize the topics which we learned in this course, and then you can maybe see whether you have any doubt in any particular topic. So so in the so basically, so this course started with a introduction to negative feedback, isn't it? And you learned about it. You learned about the basic principle of negative feedback, and you also learned some analogy how, I mean, why is negative feedback required anywhere, and what is the use of negative feedback in control systems. So negative feedback is a very important concept, and it is the like backbone of any control system. You want to control something to achieve a certain goal, right? Then you require a certain kind of feedback to ensure that you are indeed going in the direction that you are required to go. So this is like the backbone of any control systems, and you learned about how to use it. Sorry, then you learned about the block level implementation of negative feedback. You learned about the block level implementation of any control system. using negative feedback, right? You learned about the different blocks, isn't it? Like the integrate, like the sorry, the error uh, amplifier, the integrator, the buffer. You also learned about the sensor, which basically senses the output, right? So you also learned about sensor and so on, right? So this error amplifier is basically the part where you add things, right? This is basically the not error amplifier but difference amplifier, you can say, the block which takes the difference. Generally, we take this error amplifier integrator, and these two jobs are performed by a single block, which is a differential amplifier, right? And then there is a buffer, the sensor, and all things like that. So you learned about everything in that at the block level. Then you learned about the this thing. Learned about the effect of delay, right? Effect of delay in a negative feedback system. And you saw that this delay is a is basically it pushes the negative feedback system into a chaotic state, right? I mean, it starts to make the system unstable. The negative feedback system might not even reach the steady state if the delay in the system is very large, right? It pushes the control system uh, in the on the verge of instability, isn't it? So you remember this, right? All of you.
Yes, sir.
Yeah. So, so this is a problem, right? So because of that, you saw. I mean, you also you learned about this delay in the absolute sense, right? You first learned about absolute delay in the system, and you saw did some calculations, and we saw that the delay has to be limited, right? It should be under some limit, certain limit, for the system to be stable. If it exceeds that limit, the system will start oscillating, isn't it? And the oscillations can even grow, correct? So these things you learned, did some calculations to find the upper bound, sorry, on the delay in a negative feedback system for it to be stable, correct? You learned about all this, and then you saw that after that we basically understood that this delay cannot, this ideal delay is rarely seen in the system. Ideal delay is not something which is seen in the system. The delay is generally introduced by what we call as poles and zeros, right? This is what we saw. So then you next thing what you saw is delay as a result of poles and zeros, right? So these poles and zeros, they can cause problem, right? You also learned about the intuition behind pole acting as a delay, right? What was it? Can someone tell? What happens because of a pole? Yeah, anyone?
Delay due to phase delay.
Yeah, so right. So basically, what pole does is that it introduces a phase delay, isn't it? A pole introduces a fixed phase delay, correct? Now because that phase delay, it affects different frequencies differently, right? A phase delay is like what? You remember this? Let's see this, cos of omega t plus some phi, right? So this phi is a phase delay, isn't it? Correct. Now this
Yeah.
phi, if you take t outside, then this becomes omega plus phi over t, right? Sorry, my bad. If you take omega outside, then this becomes what? T plus phi by omega, correct? So now this term phi by omega, it acts as a delay, right? T plus something, or let's say it is t minus, then this is t minus. Now this phi by omega is the delay, right?
Yes.
So now clearly this phase, if phase phi is some number, then depending upon the omega value, depending on the frequency of interest, the absolute delay will differ, right? For the same phase delay, the absolute delay will differ based on the frequency, isn't it? You understand
Yes, sir.
it?
Yeah.
Correct. So that is why this the pole, what pole does is that it introduces a fixed phase delay. Okay. Now that phase delay, it translates to different absolute time delay for different frequencies. Okay. So what generally happens is that what, because of so basically still you can say that for very high frequencies, uh, sorry, so still you can say that in some sense this pole acts as a delay, right? We saw that this acts as a delay. It's just that the delay is different for different frequencies, isn't it? Right? Okay. So now this pole acts as a delay, that is okay. Now how does zero act as a delay? I mean, does it act as a delay or at all? I mean, zero. Does it depend? The zero being zero acting as a delay. Is that statement correct?
You will act as a phase lead, sir.
Not necessarily. Okay, let's do this. S minus some z. Okay, and divided by whatever you say, s plus p1, or let's call it s plus p. Okay, this is one system, h1 of s. So you take one system h1 of s minus z divided by s plus p. Okay, and another system is h2 of s, which is s plus z divided by s plus p. Now tell me in which system what so what is the zero in both the system? Zero location. What is the zero location here?
Here it is plus z, sir. Here it is minus
Correct. And here it is
minus z.
minus z. And tell me what will happen to the phase of this h1s due to the zero?
Due to zero, it will I think it will add, sir.
It will?
Add positive, no, sir.
I don't think so. Why should it add in the phase? So what will be the phase of this? Tell me, h1 of s. What is the phase?
180 degrees minus.
180 degrees?
I don't know, sir.
How come? Why on 180 degree?
No, I'm saying phase multi, sir. Sorry. Yeah, minus s by z, sir. Minus s minus z.
Minus
Tan inverse. Tan inverse.
s by
Z.
z, right? And then minus
Minus
tan inverse
tan inverse. Yes, by
s
p.
by p, correct. So what do you think? What is happening here?
I mean, here it is adding, no, sir.
It is reducing, nah. It is
Ah,
acting
yeah.
just like this pole, isn't it? It is reducing. There is a minus sign here, right?
Yeah, yeah. Yes, sir.
So this zero, which is in the right half plane, this is plus z, right? So this zero is a right half plane zero, isn't it? So RHP zero introduces what? Phase,
Phase lag.
correct. And what about here? What should happen here?
It will increase, sir. Opposite to that.
What will be this one? H2 of S angle?
Yeah, sir, it would be plus tan inverse S of Z by minus tan inverse S by P, sir. Equivalent.
Correct. Tan inverse S by P. Correct. So here it will be what?
Phase lead.
Correct. So it is a LHP 0, isn't it? Left half plane 0. So LHP 0 introduces
Phase lead.
phase lead. Correct. So this is the basic difference. So what 0 does is that if it is a right half plane 0, it will basically introduce a lag in the system, right? There will be a delay in the system because of a right half plane 0. But if it is a left half plane 0, then it will introduce, it will actually advance the system, isn't it? Phase lead means it is advancing the system. And I also gave you an intuition behind it. So can someone say what intuition I gave for this left half plane 0, right half plane 0 acting as a delay and as a advancement? Can anyone say?
Sir, if we give a step input
Uh-huh.
for left of lane 0, it
Uh-huh.
reach at steady state it reaches to the step. This is
No,
the
no.
left of.
Okay, 1 second. Let's do this. So we have this, and we have, okay, and I have given this step input. Okay, this is the step input for both the systems. Okay, so this is a case for this is time. Okay, this is time. This is V out, V out. So this corresponds to what? H1 is H1 of S, and this corresponds to H2 of S. No, not for this. Let's say that this is RHP 0, this plot, and this is LHP 0. Now tell me what will be the output in both the systems?
Sir, for the second system, the output will be like at steady state. The output will be the input.
Okay, this is the input. Okay, at steady state it is the same. Okay, fine. And
And the charging will be like exponential if RC circuit is there.
yeah, fine. So, but what happens to the 0 location? If it is a left half plane 0 and right half plane 0, what happens because of that?
Sir, left half plane 0 means if the system is stable, sir. Right half plane 0 means the system is unstable.
No, that is not true. That is true with the poles. If it is a right half plane pole, then the system is unstable. If it is a left half plane pole, then
Sir, for
then the
right
system is
of
stable.
10 0, the steady state output will not follow the input, like it will
No, that is not true.
opposite.
That is not true. So you remember what I said? I mean, for the left half plane 0, what happens is that the system gets a boost in the right direction, right? If the system steady state is this one, system will get a boost initially, and then it will start doing this. Okay.
Yes, yes,
If it is
yes.
if it is a right half plane 0, then the system will get a boost in the wrong direction. Okay, and then from there it will again start going back. So clearly there is a difference in the steady state. So the time that it requires to achieve the steady state, isn't it? So clearly this system is faster, right?
Yes,
The
sir. Yes.
transient time is faster, sir.
Yeah, correct. That is what I was looking for. Anyway, so this is the effect of poles and 0 on the delay in the system. Okay, fine. So you learned about this, and then what did you see? You learned about the concept of mm, loop gain, isn't it? Learned about what is loop gain. So this is an important concept. So this is the crux of the whole
Sir,
course.
sir,
Yeah.
one question. Sir, to find the stability or like phase margin or gain margin, we need loop gain Bode plot, right?
Yeah.
Sir, can we say the closed loop transfer function Bode plot? Can comment on the stability by looking the closed loop transfer function Bode plot.
Bode plot. You can actually what is the So closed loop
Actually, sir,
transfer function,
we don't really generally do that. Right? We use loop
yeah,
gain
yeah,
transfer
yeah,
function.
yeah, 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 right. So the reason, if you have the closed loop transfer function, then there is no need of loop gain. That is the, so why did we go into the loop gain business? Because that was easier to calculate and easier to quantify. This closed loop transfer function is something which we require actually. Okay, closed loop transfer function is the one that is the correct one, and that is the final thing. That is the final verdict. Okay, if you have the closed loop transfer function, then there is nothing to do. That is the best that you can get. But the thing is that always calculating closed loop transfer function is not easy. It is not something which is usually done. It is difficult to this thing characterize also. So that is why people go for this loop gain thing. That is easier and that is better thing to do. So
Okay, okay,
okay, if you have the closed loop transfer function, it is very good because that is the best that you can have. That there they can you can directly say that if the system is if that closed loop transfer functions pole is in the right half plane, the system is unstable. Okay, and if it is in the left half plane, then the system
okay,
is stable. That is the best that you can get. Okay,
okay, okay.
fine.
And sir, if in the closed loop transfer function, if there exist like a dominant pole concept, though, so we can then we can say the bandwidth, like the dominant pole is the bandwidth. Can we say
Yes,
yes?
yes,
Okay,
yeah. So yeah, you learned about loop gain, and here you learned about different things, right? I mean, you learned about unity gain, bandwidth. You learned about what else? Uh, no, that is oh yeah, DC gain, things like that. Steady state error. You learned about steady state error. No, this is not the part. You learned about DC gain and unity gain bandwidth. Fine. After that, you learned about Nyquist criteria, stability criteria. Correct. And based on this Nyquist stability criteria, came up uh, with the this thing necessary. Basically, we came up with the necessary conditions for stability in the loop gain. Came up with the necessary constraints of constraints on the loop gain for systems stability, right? These things we learned. Then now you learned about, after that what did you see? Learned about, again we came back, revisited the point where we left, right? The delay, sorry, effect of poles and zeros in the system, right? So they introduced instability. So how do we take care of that? So you learned about different compensation schemes, correct? Learned about dominant pole compensation, right? Moreover, we also thought about increasing the DC gain of the loop, right? DC gain of the loop gain, right? The DC value of the loop gain we wanted to increase. That, and why was that required, by the way? Why do we want to increase the DC gain of the loop gain? DC value of the loop gain.
sir. Sir, like steady state error will be less
Yeah,
if the
correct,
decision is
correct. So DC gain increasing means steady state error is reducing, correct? Fine. So we also came up with, we also looked at different schemes to increase the DC gain, right? And the most famous one, the most common and most obvious one is that cascade multiple stage, right? Cascade multiple amplifier stages, right? But then again, there when you cascade different stages, you run into the problem of multiple poles in the system, right? Remember that because of one
Yes, sir.
amplifier you get one or two poles. You cascade multiple stages, then then you have different poles, right? So how do you take care of that? By Miller compensation, right? Fine. Remember this, that if you have one amplifier only, if you have just one amplifier and a buffer here, sorry, and a buffer here, then the system has only one pole, right? Here, a pole here, correct? There is only one pole here, and by the way, this is, let's say there is a resistor divider here. Fine, this is the condition here. There is only one pole here, correct? But when you, and suppose if you want to increase the gain of the system, maybe you will start cascading different stages, right? So maybe this is the first stage here, or after this you want a second stage here, okay? And then you put a buffer here, then you put a resistor divider here, and this is somewhat like this, and this is plus, this is minus, let's say this is plus, minus is here, okay? When you do that, you see that there is a pole here, P1, and there is a pole here also, P2, right? That's the problem, isn't it?
Yes, sir.
Yeah. So what will you do? You put a Miller compensation here, isn't it? By the way, let's do this. Then you put a Miller compensation here, isn't it? And that takes care of the problem. Okay? Is this okay, right?
Yeah.
Yes, sir.
Yeah, fine. So, yeah, so moving on, we learned about these things, and from after that, I guess this was done. Yeah, you did some further calculations to reach the value of. So basically, this has, you analyze this two-stage Miller compensator op amp in detail, isn't it? You analyze this two-stage Miller
Sir,
compensator op amp in detail. Yeah.
sir, what is the like main reason to use the Miller compensation capacitor, like Miller cap? What is the main reason?
As I said, no, this is like you're compensating the system. You are trying to make an unstable system stable. I mean, let's say you have two poles which are close by. What this Miller compensation does is that it
Oh yes,
pushes
yes,
this
yes, yes.
pole
One pole
apart,
is
isn't
lower
it?
and yes, pole splitting. Yes, yes.
Correct, right? So this is why it is done, right? Then after that, you analyzed Miller compensation in great detail. You learned about the different, how many poles are there. I mean, the one that you saw, the Miller compensation network that you saw, how many
The
poles
two
were there?
poles,
Two
two
poles, right?
poles.
Two poles, and anything else?
One right up then zero.
Correct. One RHP 0. So this is not good, right? RHP 0, as we just saw, RHP 0 introduces delay, right? And
Yes,
delay leads to what?
instability.
Correct.
Like
So that is why it is not good. So what did we do to take care of this RHP 0?
so we add a register with series in the Miller cap.
Correct. So we added a 0 cancelling resistor, right? Fine. And where is that added? Let's say this is the second stage, and this is the capacitor here. So where is that 0 added?
Sir, the resistance is added in series with the Miller cap.
Correct. So here we added here, right? And what is the value of this resistor?
Sir, 1 over GM2. It's
1 over
around.
GM2. Correct. And what happens if I increase the value of RZ further more than this value? What will happen? Tell me.
Sir, I
So what?
think the zero will be in left of plane.
Yes, right. So so if we increase the value of RZ more than 1 over GM2, then the resulting zero comes in the left half plane, isn't it? So it's a good
Yes,
thing,
sir.
right?
Yes.
Left half plane 0 is a good thing, right?
Yes, sir.
So why don't we make it infinity? And why do
Because the power dissipation will be more, like
no no
resistor.
no 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 power, there is no power dissipation here. There is no power, there is no current flowing here, isn't it? There is no bias current is not flowing here, isn't it? So what is the problem?
Sir, once a third pole will be there
Yeah,
and
right.
pole
There will be a third pole in the system,
from
okay? And that is not good. There is third pole, and that is approximately at the location what? There is a P3, and which will be at RZ into what?
C.
Series of CC, CL, and again this thing right here, right? C1, isn't it?
Yes, sir.
And this will start dominating. This P3 will start coming into picture. So you cannot increase RZ to a very large value and think that the system will start becoming very stable, because this pole P3, it will start coming in the picture, which you do not like, right?
Yes, sir. Yes.
Yeah. Also, you can clearly see that if you now, if even if you don't know about this pole P3, you can understand it that if I increase RZ to a very large value, okay, like what is the limiting value of a large value? What is the limiting thing of a large value? Infinity, isn't it?
Yes,
Something
sir.
Yes.
cannot be larger than infinity, right? So,
Yes, sir.
so that is why if this RZ becomes infinity, what will happen? This is as good as saying that this connection is not there, isn't it? What is
Yes, sir.
infinite resistance between two things means? There is no connection, right? Right now,
Yes, sir.
yeah. So basically, this Miller compensation is lost, isn't it? So
Yes.
it is like this Miller compensation is not there. So basically, the you will again end up with the old case that you have this pole and this.
Cascade.
Basically, you have a cascade of two poles, right? So these two poles will become independent in that limiting case. So because of this RZ, what happens is that RZ introduces a third pole, and it also has an effect on the two poles, okay, two other poles which were initially apart, far apart. They'll start coming closer, okay.
Yes, sir.
Okay, fine. So after that, what did you do? So this was it for the whole two-stage amplifier. Yeah, you also learnt about this feed-forward thing, right? You also learned about feed-forward compensation, correct? And what do we do in a feed-forward compensation? We have a slow path, right? And we have a fast path. You join these two, correct? Right now,
Yes, sir.
Yes, sir.
correct? We have this is slow path. Why do I call this as a slow path and this is the fast path? Yeah, go on.
Sir,
Tell me.
upper path has two time delay elements like.
Correct. So this has two delay elements, right? This is slow path. There are two delay elements. This is a pole. This is a pole. Correct. A pole means a delay element. Correct. It's like that.
Yes,
It is a like it is like this is one analogy that there is the delay will be larger if you have more poles in the system. Okay, fine. But the bottom one has only one delay element. I mean one pole, right? Only this CL. Correct. So this is
yes,
definitely fast. Correct. Fine. And what happens? How does things work? How do things work? What did you learn? I mean, how does feed forward compensation work? Or any amplifier using this made using this feed forward thing? How does it work? So let's say you have this V in, okay, and yeah, and this let's say is V out. So how does this work? Try to remember. What happens? It was like this, right? That initial. What is the what? Why did we do this? By the way, feed forward thing. It was to how
Push more current into
what?
push more current into the output conductance so that
Yeah, correct. So basically, you see that using a single stage, okay, you will not get as much gain, right? As much DC gain possible, correct? And there will be error between these two, correct? These two, right? So what? Let's say you have an output conductance here, or put it here. Okay, this is let's say some output resistance GL. Okay, and using a single stage here, you will not be able to you will not be able to achieve that much of DC gain, right? And what will happen basically, this will require some current to have some a certain voltage here V out. Okay, V out times GL current is required, right, to be flowing in this, correct? Now that current has to come from this. If this path is not there, if the upper slope path is not there, then that current has to come through this fast path, isn't it? Right?
Yes, sir.
yes,
And that this fast path, since it does not have a large gain, it means that the difference between these two has to be very large, isn't it? Because the current in this will be directly proportional to the difference here, right? This is a current voltage controlled current source, right? Let's say it has GMF. So what will be the current here? Current I will be GMF times this difference delta V, right? Will be current. And if this current is equal to GL times V out, then what will be V out? V out will be GMF divided by GL into delta V, right? So if you require larger V out, that means you will have larger delta V, and delta V is the error, right? You require the error to be lesser and lesser, correct?
yes, sir.
Yes, sir.
But if you require certain V out, then that is not possible. If you require a large V out, that is not possible. So that is why this is not a good thing, right? So what do? What we did was that we said that okay, let this do its job. Let this fast path uh, do its job instantaneously when you switch on the circuit, and after it has reached its steady state, okay, after this fast path has done its job, what we'll do is that we will activate this slow path. Okay, what it will do is that it will start seeing what is the error here, which is delta V. Okay, which is delta V, this one delta V, and based on this delta V, it will start to compensate this delta V by pushing more current into GL, so that this delta V reduces. You understand? I mean, this was what was taught in the lectures also, right?
Yes, sir.
Correct. So this is how it works. So fast path, that is why it is called the fast path, because this works almost instantaneously. This acts very fast because there is only one stage here, and once it has reached a steady state, this fast path, after that the slow path has to take over. So the slow path has to be much slower compared to the fast path. Otherwise, these two loops will start competing with each other. Hmm. Understood? Fine. So you
Yes,
understood,
sir.
right?
Yes, sir.
This feed forward compensation. Yeah. So after this, what we did learn? Yeah. After this, we went to the noise thing, right? And what noise? Correct. So you learned about thermal noise. You learned about flicker noise, right? So, so what is thermal noise of a resistor? Spectral. So yeah, okay. So before that, now this thermal noise, all these things, these are random, right? Noise is a random process. So you cannot definitely characterize it since it is a random thing, and it is not. What is random? Random is something which you cannot confidently say about, right? That it will happen. It is this value. You cannot guarantee that value, right? For a random thing. Random thing is it will be. It can take any value at any point of time, and you cannot uh, you cannot guarantee it before seeing at the value, right? You understand?
Yes, sir.
Yes, sir.
Right? So that is why noise is a random process, and that is why we try to all the random things we want to characterize using their statistical parameters, right? So since it is a random process, we characterize it using uh, statistical parameters. And what are those parameters?
Power spectral density.
Yeah, and okay, so in the time, okay, fine. So it is basically power spectral density. Yes, we also learned about the mean, right? Mean of any random variable, that is also one measure, right?
Yes. And
Correct.
variance.
Variance, correct. So variance is also another thing. So this variance actually, this variance, right? Variance also we calculate. Fine. Now there is one important thing. We basically variance and mean are the special cases of a much broader this thing, broader concept, which is basically correlation, right? We try to learn about the correlation. So basically this this variance is a special case of autocorrelation, right? Do you know about these things? Do you know about these things? Autocorrelation, have you heard this word?
Yes,
Yes,
sir.
sir.
Okay, so I didn't hear a lot of yes, so maybe this is not required to be taught here, so ignore this in that case. Forget this. So you learned about PhD, right? Power spectral density. And what does PhD mean? What is PhD?
Sir,
Power
power
delivered
over
to
a
the
frequency range.
power delivered
Power,
to the load by the
spectral
noise.
density. What is it? Power per unit frequency, right?
Yes, sir.
Yes, sir.
Right? Fine. So, what is the PhD voltage PhD of a resistor?
Sir, 4 kTR.
Is equal to what? 4 kTr. What is K?
Boltzmann constant.
Boltzmann constant.
Yes. What is T?
Absolute temperature.
Yeah, fine. Fine. And fine. R is the resistance. Fine. What is the PhD of a MOSFET?
Sir,
8
8.
by
First of all, for a MOSFET, are you saying voltage PhD or current PhD?
Sir, voltage PhD will be in saturation like 8 by 3 kT into 1 over Gm.
So, but we generally talk about we don't say MOSFETs this thing. MOSFETs voltage PhD. We talk about MOSFETs current PhD. Okay, that is
Okay.
actually what is
Yes.
calculated. This voltage is something which we referred it back. Okay, that is not
Yes.
actually there.
Yes, sir.
The current PhD is the thing that you should talk about. Okay, so
Yes, sir.
MOSFET current PhD is what? For MOSFET current is like this, right? You say that there is V in and there is this, other than the already present current here, there is the current here also, right? Which is what? 4 kT gamma gm, right? Right.
Yes, sir.
And this gamma for long channel devices, it is what? 2 by 3, right?
Yes.
For short channel devices, gamma value is larger. Okay, it is slightly larger. It is approximately 1, close to 1. Okay, fine. So that is fine. Now you also saw some questions and conditions of this questions pertaining to this noise. Okay, learned about how noise behaves. You learned about the KTYC noise, right? You learned about this KTYC noise, isn't it?
Yes, sir. Integrated like
Yeah, correct. This is the integrated noise of a simple RC
resistor.
circuit.
RC. Yes. RC.
So basically this is V out noise, right? KTYC, total noise power is KTYC, right? Fine. Uh, Move. What else? What else? Yeah. After this, you learned about mismatch. Correct. Right. You learned about
yes, sir.
how. Yeah. Any question?
No, sir. I'm just.
Okay. You learned about modeling mismatch. Correct. So mismatch can be in what quantities in a MOSFET? It can be a threshold voltage mismatch, right? It can be threshold voltage mismatch, or it can be what?
And it
Huh?
be beta mismatch.
Yeah, it can be beta mismatch. So you learned about these things, you learned about how to model them, you did some calculations, and what did you find out? Moreover, this mismatch is inversely proportional to what? Sigma is inversely proportional to what?
Area.
Correct. Right? This is the thing that you should remember after this. This is a very important thing. You should remember this. This mismatch sigma is inversely proportional to area. Okay, fine. Also, this flicker noise. Where is that flicker noise? Yeah, this flicker noise also, it is inversely proportional to what? Length,
Omega
right?
into LO.
Right. I mean, yeah, it is definitely inversely proportional to frequency. That is true. But yeah, again, it is also inversely proportional to length, right? So, in general, people when for very low frequency designs, okay, where the frequency of operation is very low, like your pacemaker in the heart, okay, pacemaker and things like that, which are very low frequency requirements. There, the flicker noise is a very serious problem. Okay, so there generally people use very large length devices. Okay, so that flicker noise is not a problem, and generally it happens that for very low frequency devices, the precision is very precision is the concern. Okay, precision is a concern, so mismatch is also a problem there. So there people generally use large length and large width, so that sigma is very small. The mismatch is not a very large, the mismatch is really not large in that, if w and l are both size larger. Okay, fine, so that is okay. So you learned about mismatch also, and fine. So what else after that? I guess after that you learned about the transistor level implementations of the amp. So you learned about some basic amplifier, single stage amplifiers, right? Right, like common source, common drain, and common gate, right? Learned about these three. Fine, fine. You also learned about this additional thing like source degenerated. Fine. After that, you learned about cascode, right? Cascodes. You also learned about telescopic cascodes. Also learned about folded cascodes. Fine. So there is no issue here, right? Cascode, telescopic cascode, folded cascode, CSCD, CG, all these things are clear to you. Finally, you learned about the transistor level implementation of
Sir, for telescopic and folded cascode, we need to remember the data sheet, or we can derive at the time, sir.
what data sheet? What do you mean by data sheet?
Data sheet. At the end, for every for a telescopic, at the end, Anirudhan sir will make it as a data sheet, no sir. Everything
You
in.
can remember it. It will be handy for you if you remember it. Otherwise, you can always calculate it. Doesn't matter. If you understood the concepts very well, then you can always calculate it. But you can also remember it. It comes in handy in interviews. Okay, interview will not have time to derive it, right? So there you require, you should have this on your fingertips. So, so there, for if you are targeting some interview, then it will help you. Even in the
Yes.
exams, it will help you because there is a time constraint in the exam, so it will help you. Anyway, so finally, you in the week 12
So
continue to,
small question, sir.
yeah,
Sir, sir, like that is modeling and all. Before that, first 6 weeks, sir.
yeah.
The same textbook, sir, for that one also. Razavi.
I didn't get your question.
For reference book for first that Miller
Yeah, yeah,
compensation stage.
yeah. There is it is also covered in Razavi's book. Yes. Okay. Okay. Yeah. So in week 12, we learned about the transistor level implementation of a two-stage Miller compensated amplifier, right? So this is all that you have learned in this course, right? Learned about negative feedback and then noise mismatch, transistor level implementation of a differential amplifier. Okay, so this course is aimed at equipping you with the necessary knowledge that you require for building a an operation amplifier on your own. Okay, so what all things you have to consider while designing an operation amplifier, all these things are covered in this course. Like you have to be careful about the mismatch, you have to be careful about the noise of that op amp, right? These are covered in the all these things are covered in this course. So any doubt? So there is a okay. So one second. Yeah. So Vasu, I do not know what is going to the pattern in this of the exam. Okay, that is I do not know. Okay, so that only the instructor knows. I do not know about it. Okay, fine.
Sir, the question will be like MCQ types. So
I have no idea. I have no idea.
okay, okay sir.
Okay. Okay. So the how to design an op amp when all the specs are given. So this is the question. Okay. So fine.
She said
Let's do
like
that.
how to start the designing. Yes.
Hmm, let's see. Okay. So let's say you have to you there is a question there you get a design problem. Okay, you have to design an op amp which is a two-stage op amp. Okay, and you will be given a certain amount of load, capacitive CL load and the resistive load RL. You will be given that you have to drive. Okay, you'll also be given what will be the what should be the UGB. Okay, you will also be given the UGB. You will be given the maximum power dissipation. Okay, what is the maximum power dissipation that you can have in the circuit? You will be given what is the required phase margin. Okay, you will given that by these are all the specs, by the way. These are all the specs. Okay, you will be given what is the phase margin required. You will be given what is the minimum DC gain. Okay, fine. All these things will be given to you. More than this, you will also be given the noise requirement. Okay, you will given the noise requirement. You will given the uh, so in some advanced designs you will also be given what will be the what should be the this thing. Mm, because what will happen, this random mismatches, because of that the specs that you will be targeting, it will differ, the design will differ from IC to IC, right? Because of the mismatch. So you will also be given a 3 sigma requirement, like what should be the mis even if you fabricate like 100 ICs, so you will it will be given that 99% of the IC should be behaving in this particular manner. So all that will be given to you, and after that you will start designing. Okay, so let's say you have this two-stage op amp, this architecture is given. So now you have to decide for the first stage. So basically this is a two-stage amplifier, right? And this will be RL, this will be CL, right? And Please remember that this will also have its own G2, right? If this is GM2, this is GM1, this will have its own G2, this will have its own G1, right? There will be C1, correct? Fine. Okay. So now when you are given CL and RL, this is given to you, right? And you have been given UGB of the system. So UGB is what? GM1 by CC, right? Hello.
Yes, sir. Yes.
Yeah. UGB is what? GM1 by CC, correct? So from this, what you will do is that you will have to assume some value for CC and GM1. I mean, you will have to assume certain value for CC, or you can assume certain value for GM1. Both ways it can go. Okay. So if you assume certain value of GM1 or CC, then you can calculate the other one, right? Let's say you have assumed certain value for CC, then you can calculate GM1 based on the UGB requirement, right? But if you have, let's say you have
Yes.
assumed GM1 value, then you can calculate CC based on the UGB requirement, right? So it can go both ways. So you'll have to assume certain parameter and then obtain the other parameter based on the required specs. Okay. Now once you have done that, GM1 is fixed to you and and CC is also fixed, right? Now you require certain DC gain, right? In order to have a large DC gain, you will have to take a call whether you require cascode somewhere or not. Like this GM1, how will you make this GM1? You can use this, right? Sorry. This is GM1, right? Oh, sorry, this is not grounded, but this is like this, correct? This is GM1. Now, but let's say you require larger gain from this. Okay, by the way, the second stage will be how will be the second stage? This will be like this, right? This is the second stage, isn't it? And you will have a CC here,
Yes, sir.
right? And this will be out. Anyway, there will be CL here and RL here. This is V out. Fine. And now let's say the total DC gain will be what? The gain of the first stage and the gain of the second stage, right? True.
Yes, sir.
Right. Now let's say you require larger amount of gain from the let's say the total gain here, which is the product of the first and second stages gain, is not enough. Okay. So you want to increase the DC gain of the system. So what you can do?
Cascoding.
Yeah,
It
even before
telescope
cascoding,
property.
there is an obvious solution, right? Even before cascoding, let's think. So this second stage gain you can increase, right? Because the second stage gain is being limited
Yes.
by this RL, right? So if you start increasing GM values here, if you start increasing the GM of the second stage, then you can increase the gain, right?
Yes.
What is the second stage gain? GM of the second stage, let's say it is GM2 divided by what? RL, right? Sorry, GM2 into
Yes,
RL,
sir.
right? I mean, there will be G2 here, but let's say this G2 is much larger compared to 1 over RL. So that this overall resistance is dominated by this RL. Okay. In that case, the gain here will be GM2 times RL, right? So if you start increasing GM2, your gain should increase, right?
Yes, sir.
Yes. Yes.
Sir.
But what will happen if you start increasing GM2? How will you increase GM2?
Power dissipation.
Power
Yeah,
distribution
right.
is more.
So power dissipation is also a constraint here, right? So you can definitely not increase it beyond a certain value, correct? So the
Yes.
another solution is, why don't I cascode? So which one should I cascode? This one or this one? Where should I cascode?
The first one, I guess.
Yeah, I mean, okay, so why not both? I mean, who is stopping me for cascoding both stages, right? If I want large gain, I will simply cascode both the stages. So which is
String
preferred, by
limits,
the way?
because I think the first stage,
The
because
second
if you
stage is
cascode the
limited
second,
by RL.
Tell me, come again.
Sir,
first
the
stage, I
drawback
think.
of cascading is we are compromising on swing. So if we cascade on second stage, then output voltage swing is compromised. So
Correct,
we don't
correct,
want to
correct.
go for
Yes,
Very good,
yes,
very,
yes.
very good, very good. So there are two reasons to not doing this. Okay, output stage, you are not cascading because of two main reasons. So second stage, cascading is not preferred for two reasons. First of all, which is the main obvious reason, is that gain may be limited by RL, right? Fine. So by
Yes,
the
sir.
way,
So
Yes,
please remember that gain being limited by RL is not a good thing. Okay, when you start or designing certain thing, this RL will not be in your control. Okay, so this RL is, by the way, when you have this whole op amp. Okay, the whole block, when you have the whole block, this RL is basically this thing. This is 1R and this is 1R. So this is basically RL. Okay, so this op amp here should function independently of this what value of RL you choose here, right now.
Yes, sir. Yes,
So
sir.
the gain of this whole op amp should be ideally independent of RL. So gain depending upon RL is not a very good thing. So here when I wrote that this gain is being limited by RL, it was just to make your life comfortable, just to ask my question. But in actuality, the gain of this whole op amp should not be a function of RL. So what is the best thing to do? You have to increase G2, right? I mean, this GM2 is generally sized very large in that case, so that the G2 here is much larger. G2 here is much larger than 1 over RL. Okay, so that gain is limited by G2 and not RL. Okay, the gain is limited by the output resistance of this second stage and not by the resistance RL. Okay, fine.
Yes, sir. Yes,
Yeah,
sir.
but let's say even if when you ensure that even when you ensure that after that there is no point in cascoding it, because when you cascode it, the resistance decreases, right? The output G2 decreases this by cascoding it. So it may happen that this cascoding is not proving helpful, because ultimately the effective resistance is dominated by this RL. So this is one of the reasons, one of the first reason. This is the first reason for not preferring cascoding at the output stage. But the main reason, for not preferring output cascoding is the swing limit. Okay, swing is limited. Swing is limited. What swing? Output swing. Output swing is limited by cascoding the second stage. You understand this?
yes, sir.
Yes,
If you
sir.
put larger number of stages here, then what will happen? If you put another stage here, the swing will be reducing, right? Correct?
Yes, sir.
Yes, sir.
Yeah. So these two are the reasons that you do not prefer cascoding at the output stage. So then in that case, what will you do? You will simply put cascoding here, right? Right?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yeah. So fine. So based on the DC gain requirements, you'll have to take this call whether or not to put cascoding at the cascoding in the first stage. Okay, you'll have to take this call. Okay, fine. Now okay, now once you have made that decision whether or not to use cascode or not, After that, and you also know what is the value of GM1 and CC, right? So when you use cascode and even without cascode, now you'll have to size this particular transistor. This is the input, right? So GM1 will be the GM of these two transistors, right? GM1 will be what? GM of this, right?
Yes, sir.
So
Yes, sir.
now you will have to size these two transistors for certain value of GM. Okay. Okay. Size means what? You will have to find the required current that needs to flow and the required W by L that you require that you need to have here to make sure that you get certain value of GM. You know what is GM, right? GM is root over I naught into mu 1 Cox W over L 2 I naught, right? Where I naught is the current flowing in the transistor, right?
Yes, sir.
So you have to find out what should be the current and what should be W by L for getting this particular value of GM. Fine. Fine. Once you do that, now when you connect everything in the feedback, now you have to find out what is the UGB of the loop gain. Okay. You have to see what is the UGB, whether you are indeed getting the UGB that is required or not. I mean, you calculated the UGB, right? GM1 by CC. You calculated it and you designed it such that you need to get that particular value of GM1, correct? But when you connect everything in feedback, you will see that maybe you are not getting that, correct?
Yes, sir.
This will happen. I mean, you have calculated something and you start designing it, you connected everything together, and then when you connected and again saw the response, you will observe that the overall response is not what you predicted. It will be slightly different, so we'll have to go and start tweaking things here and there. But before that, I didn't talk about how should you size GM2. Okay, I only said that you have to keep GM2 very large. Okay, now what is the constraint on GM2? What all things are dependent upon the value of GM2?
Sir, overall
The
DC
zero
gain.
zero frequency depends on GM2.
Fine, let's
And
see.
parasitic force.
So let's see. P2 is equal to what? GM2 by approximately equal to what? GM2 by CL, right?
R R output.
Huh? R out. No, P2, pole P2 location is GM2 by CL, right?
Yes, sir. Yes. Yes, sir.
Yeah,
Yes.
fine. Okay. Now, okay. And what is phase margin? Remember? Okay, first before that, what is zero location? GM 1
GM2
over
by
GM.
CC.
Yeah, GM2 by.
GM2 by CC.
Yeah, fine. Now, what is the phase margin? GM2 by GM1, right? Tan inverse GM2 by GM1, something like that. Remember? What will it be? Tan inverse. What is it?
Sir, 180 minus like tan inverse G GM2 by G1, like, yes, again minus tan inverse uh, unity loop unity gain frequency by
Okay,
0.
let's do this. So, what is the phase? How will you calculate phase margin? It is 180 degree minus tan inverse. What is pole P1? P1 is actually 90 degree. Okay, first pole has already hit, so remove this. Minus tan inverse. There is only this second pole, right? Second pole is GM2 by or UGB by P2, right? What is UGB? GM1 by CC divided by P2, which is GM2 by CL, correct?
Yes, sir.
And minus tan inverse zero location, right? Which is GM1 by GM2. So it is actually GM1 by CC divided by GM2 by CC, right? CC and CC
Yes, sir.
cancel. So it is actually equal to 90 degree minus tan inverse gm1 by gm2 into L over cc minus tan inverse of gm1 by gm2. Fine. So clearly, if you want to increase the phase margin, gm2 should be very low, right? Very high, right? This guy, this is minus tan inverse, right? So this should be as low as possible, right? This should be as low as possible. For that, gm2 has to be as high as possible, correct? So
Yes,
you
sir.
want to increase gm2, correct?
Yes.
Right? But let's say, okay, here this second term is because of the zero, right? So we already learned what we can do of this zero. What should I do?
Sir, GM2 much greater than GM1.
No, that is
Sir,
true. That is
the
true. But how will I take care of the second term? So ideally, I want this to be as small as possible, right? So what is the smallest value of that this can get? Zero, right? It cannot be smaller than zero. Here also, this also cannot be smaller than zero.
the zero
Correct?
phase must be added now, sir. Why did we subtract zero? The phase
No, this
contributed
is
by zero.
no. This
The
zero is a
height of
right half
phase
plane
0.
zero,
Right.
right?
Okay.
This is RHP zero. So RHP zero is not adding; it subtracts. I already covered this in the start of this class. I mean, this has been talked about multiple times in the whole course. Okay, so yeah, so what can I do with this zero? This is definitely true that you have to increase the value of GM2, right? But let's say even after that you are not satisfied. So what you can do?
Sir, resistors
Yeah,
with
correct. Put a resistor here, right? RZ, correct? And RZ should be equal to 1 over GM2, right?
yes, sir.
So this takes care of this term, correct? This term will not be there after that. But even then, this has to be very small. This has to be very small, right? So that overall phase margin is very good. So what will you do? You have to increase GM2, correct? Also you have to increase CC, correct? You have to increase CC, isn't it? Hello?
Yes, sir.
Yeah, you have to increase CC, right? But if you increase CC, you'll also have to increase GM1, right? So ultimately this will not have, and this is very obvious because this is basically tan inverse of this. GM1 by CC is actually a constant thing, right? You cannot change it. GM1 by CC is the UGB, and UGB is given in the specification. You cannot change the UGB, right? So all you
Yes,
can
sir.
do is increase GM2. So it is basically UGB by GM2 divided by CL, correct? So UGB is fixed. So all you can do is reduce the increase this term, right? GM2 by CL. So it is also obvious if you consider this Bode plot of this of the amplifier. So what is the Bode plot of a two-stage amplifier, Miller compensator op amp look like? It will have this, right? We will have this pole P1. After that, it will start going down here. This will be the UGB, and here somewhere you will have second pole, right? This is pole P2. Now this UGB location is fixed, right? If you want to increase the phase margin, what will you do? You will push this P2 farther apart, right? This is all you can do, right? You cannot do anything else here, isn't it?
Yes,
Yes,
Right?
sir. Yes.
And how will you push P2 farther? That will be by increasing GM2 by CL ratio, right?
yes, sir.
But
Yes.
CL again is given to you. You cannot reduce CL, right? So CL also is fixed. So what you can do, the only one thing that you can do here is that you can simply increase GM2, right? Nothing else, right now.
Yes, sir.
So
Yes,
while designing, you will have to see for a certain phase margin how much GM2 minimum GM2 you require. UGB is given to you, right? CL is given to you. This nine and based on that, and phase margin constraint is also given to you. Based on that, you will come up with a minimum value of GM2, right? Phase margin should be greater than this guy, right?
yes, sir.
Sorry. This is the phase margin. This is the phase margin, right? And it has to be greater than certain value, let's say 60 degrees. So based on, for that you will get a certain constraint of GM2, that GM2 has to be greater than certain minimum value. Okay, from there you will find the minimum value of GM2 that you require, and for that minimum value you design this transistor here, this here and this here. Okay, so that you will get a you will get all the
So,
sizes. Hello,
so I didn't
yes,
understand the last part.
okay, I'll come again. So I am saying that you understood that this is the phase margin, 90 degree minus tan inverse UGB into CL into divided by GM2. You understood that?
Yeah, yeah,
Yeah. Now I have already told that in the specification you will be told that you require to design the op amp to have a certain phase margin,
yes,
right?
yeah. So at least 60 degrees. At least.
Yeah. So what I'm saying is that now if that is given, that you have to have the certain phase margin, let's say that certain phase margin is 60 degree, that I am saying that the phase margin, that minimum phase margin that you require for this op amp is 60 degree. Okay, that will be given in the specification, and you already calculated what is the phase margin in terms of the different design parameters, right, which is UGB, CL and GM2. You know this expression, correct? Now all you need to do is that you have to uh, you have to establish this inequality, isn't it, that the phase margin should be greater than 60 degrees. That is what I have done here. Is that clear?
Okay, sir. Okay.
Now when you do that, when you put this inequality here, this inequality, when you solve it, you will get a certain, okay, so let me solve it so that it doesn't create any confusion. Okay, so from here, like this is understood, right, this inequality, that my phase margin should be greater than 60 degree. Okay, so from this what I will get, so this is 30 degree should be greater than tan inverse of UGB into CL divided by GM2, correct? And what is tan 30 is 1 over root 3, right? It should be greater than UGB into CL divided by GM2. So what I will get, GM2 should be greater than UGB into CL into root 3, isn't it? Is that clear?
Yes, sir.
Yeah. So what I've done here is that, you see, based on the phase margin requirement that I had, I calculated what is the minimum value of GM2 that I require for the certain UGB that I have to achieve. What is the minimum value of GM2 that I know that I need to have that amount of phase margin in the system. So this is what I have done here. Now when I get this GM2, based on this GM2, I will calculate what should be the size of this transistor here, right? Because this is the transistor which is acting as GM2, right?
Yes, sir.
Right. So I will have to calculate what is the WYL here, WYL here, and what should be the current that needs to flow through this. Correct? Fine.
Yes,
All
sir.
that when I do, and then I can connect it in this manner, and I will see what. So after, when you connect it in this manner, and you close the feedback around this particular op amp, you will see that this op amp behaves slightly differently than you expected. Then you have to go and tweak your op amps here and there. Okay, to achieve achieve those specification, which is UGB and phase margin, DC, and all those things. Okay. Now after you have done all that, you will maybe you will see that the noise is exceeding the value that it was supposed to be. Okay, noise is not enough. Noise is very large. So what you will have to do? So one direct, very obvious solution is that you simply scale the powers, right? When you double the power, your noise power goes down, right? Hello.
Yes, sir.
Yeah,
Yes, sir. Yeah.
fine. So that is one of your solution. Otherwise, there are many architectures which are low noise things, which focus on low noise. So those things are out of the scope of this particular course. Okay. Also, you will see that maybe your 3 sigma requirement is not meeting. Okay, the mismatch is too large, so you'll have to take care of that. So one of your solution again is that you simply size everything large, increase the W and L both. So increase the length by 2 times, make the length 2 times and W also 2 times. So nothing changes in W by L, but your overall noise, overall this mismatch, it goes down, right? Two times, by two times. So all those things you can do. If you do not want to increase the sizes, then maybe you have to go through, there are certain techniques, okay, to take care of the mismatch. All those things are out of the scope of this particular course. So you got a brief idea, right? Understanding of how to design an op amp when you are given certain specs.
Yes, sir. Yeah.
Yes, sir. Yes, sir.
Yeah, fine. So I guess that's all. I mean, anything else if you want to ask, you can ask me. Otherwise, I have nothing else to cover.
Sir, I have a doubt.
Yeah.
Sir, in the last week, sir, like sir taught us about that single rail and double rail op amps. Like
Uh-huh.
he was, he made a inverting amplifier with a single rail op amp,
Mm-hmm.
and then like we have to bias the inputs, right? Because it is
Mm-hmm.
single rail, we
Uh-huh.
cannot be zero input. So there, sir, in the load register, he gave a like bias after the RL, like what
Ah,
RL
okay.
is there. So how do we do that? Like we don't know where the that RL is coming, right? It may be from some other circuit or something like that.
Hmm. Yeah. So that is why. So basically, this RL, this bias, it will be given to you when you are designing an op amp. It will be told to you what should be the output, okay, where it will be connected and what should be the bias there. Okay. Based on that, you will have to design it. And when you connect it to any other circuit, this will look something of this kind. So as I already told you, that this resistor RL here, that the ground that I have put here, it's not actually ground here, it is incrementally ground. Actually the RL will be connected like this, okay, this here, and there will be VN here, VN here, okay, and this is also not grounded here, this is also connected to certain bias here, okay, here also this is not connected to ground but certain bias here, okay. Do you understand what I'm saying?
Yes, sir. Yes, sir.
Yeah. Now let's say this op amp is not used in this manner that I taught, that I just showed. Let's say this op amp is used like this. This op amp is here, okay, and you have this RL here, right? Now this RL, it goes maybe to uh, how, which particular example should I take?
I think
Uh,
the unity gain configuration.
yeah, so that is the best configure. That is the best example basically. So this RL here. So this is the best example. Okay, so let me just copy it and use it here again. This is the best example. Shit, remove it. It's already very bad. Remove it. Let's draw it again. So this basically what I'm saying is that, let's say you have made an op amp here. Now this RL which you have connected it, it will not be connected like that. So it will be connected in this manner. This is RL, this is RL, and you have this V in, which is small signal, and there will be a bias here. Okay, V bias. This will also be connected to some V bias, and there will be output CL here. And yeah, so by the way, this VIP and VIM that I have shown here, okay, so this is basically the VIM here, and this is VIP here, okay.
Sir,
So yeah,
sir, actually, I understood this configuration. Actually, sir showed an example with non-inverting one. There, I got confused. Like,
okay, and okay, fine. So let's talk about non-inverting amplifier. Let's say this is CL, okay. This is
and sir,
RL.
it was a buffer. Like the RL was after the output. Like from the output node, there was an RL to bias. That thing I could not understand.
This is RL, right?
Yes, sir. And that
And
RL
here you
was
require a bias,
that thing.
right?
Yes, sir.
So there are two things here. You can either you can also not use a bias here. It doesn't matter. Okay. So what happens is that uh, first of all, do you understand that you require a bias here? You understood it, right? Here,
Yes, yes, sir.
this is the input, right? Input will not work without a bias. So you have to have a bias here, correct? Okay,
Yes, yes, sir.
fine. Now at the output side, now this output is actually how this op amp. If you go inside it, if you look at it, the output of it will look something like this, right? There will be a PMOS here, and there will be an NMOS here. This will be some V bias, some bias voltage at the MOSFET input, and this will be some output, right? And there will be this capacitor CC here, and there will be this CL here, and there is a resistor here. Now this resistor, it can either be connected to bias, certain V bias, or it can be grounded also. Okay. Now what will change if you ground it? First of all, let's think about what will happen if you ground it. Let's say if it is grounded and you require this voltage here, which is this V bias plus V in, right? What will the voltage that will appear here? It will V bias plus V in, right? V in and V bias both will appear, right? The voltage here will
Yes.
be V bias plus V in, correct? Because in the this is an op amp, right? So this has to be this has to be virtually shorted, correct?
Yes, sir.
So this will be V bias plus V in, correct? So the same voltage V bias plus V in will appear here also, correct?
Yes, sir.
Right? Now if the voltage here is V bias plus V in, okay, what is the current flowing through RL?
By R, V bias plus V in by R.
Yeah, so current will be V bias plus V in by RL, correct?
Yes, sir.
Now you see what is the problem here?
Yes, sir. Power
A
dissipation.
lot of current, no, it's not even power dissipation, forget about that. A lot of current has to flow through RL. This MOSFET, this MOSFET is what? This MOSFET has to have that amount of current for it to flow through this RL, right?
Yes.
Ultimately this will be flowing through RL and this will be provided through this MOSFET, right? Oh
Yes,
shit,
sir.
this is not moving. Okay, it is not moving. There is a lag. Uh, okay, yeah, now it is moving. So I was saying that this current here, which is flowing here, has to come from this MOSFET, right?
Yes, sir.
Yeah. Now this current, if it is very large, the MOSFET, the current which will be in the MOSFET has to also be very large, isn't it?
Hmm. Yes.
Huh? Now that will simply translate to a large power dissipation in the MOSFET. Okay.
Sure.
You'll have to have a very large current flowing in the MOSFET to make sure that the current is flowing here also in the RL. So what do? How will you get rid of this bias current? This bias current can be get rid by putting a bias voltage here, right? In that case, the total current that will flow will be simply V in by RL, right? Isn't it?
Yes, sir.
Yeah.
So
So
what
does that?
I am asking is like how do we do this? This RL is of some preceding stages output impedance, right? Input impedance, right? Like if you're connecting an op amp and then some other stage after it,
Uh-huh.
then that stage will have some input impedance that would be considered as RL, right?
Right, right.
So how do we connect this V bias with that
Yeah.
RL? Like
For now, just understand that this will be a voltage source. You will have that voltage source. But if you want to have something like this, then maybe you'll have to use things like LDO and all, low dropout regulator and all. So just ignore those things. Don't get into that. Okay.
okay.
All you need to understand right now is that what is the requirement of this V bias. You understood it, right? What is the requirement of V bias?
Yes, yes.
Yeah.
So,
Yeah.
so one doubt. Yeah.
Yes.
For the if we consider the op amp in unity loop gain
Uh-huh.
configuration,
Uh-huh.
um,
Unity gain,
how
right?
is it
Not
that
unity loop gain.
CMR? See, because of CMRR, how is it some offset is produced? That part, sir did say about it, but I didn't understand. Because of
Uh,
because of the common mode voltage, how is offset produced?
if there is a mismatch in this resistances RL, then there is a offset. Then there is a this thing mismatch
Okay,
produced, right?
that would be because of the mismatch between the transistors. But sir said something about the common mode voltage would produce an equivalent some form of mismatch, some form of offset voltage at the output when operated in unity gain configuration.
Mm, I do not recall. I mean, I do not
Is
understand the
that
question that you're
possible?
asking.
Like,
I mean, yeah, if the resistances are not exactly identical, then you will have certain common mode also at the output. Okay.
the resistance where, sir?
If the resistances are not identical, okay, if the resistances are no, no, sorry, if the resistances are the resistances are mismatched, okay, then you might have certain common mode at the output, along with the input, along with the required value that you want. You also have a certain common mode. Like the output will not only be dependent upon VIP minus VIM, but it will also have this VIP plus VIM by 2 term, okay, times certain value.
So that would be if we consider R, right? So for if we don't consider that in voltage follower mode, will there be any offset due to common mode input?
If there is a voltage follower here, okay,
Yeah.
now this is a voltage follower, okay, now I don't think so. I mean, the okay, so output, what is the output here in a voltage follower? What is the output?
If we consider more or less if the op amp is ideal apart from common mode, the output would be same as the input. Yeah.
If this is a simple voltage follower, then there is no point of, then there is no concept of common mode or differential mode, right? There is only one
Sir, I
input.
think he is talking about systematic offset, which because of wrong scaling of MOSFETs inherently, even though mismatch is zero, there will
Oh,
be
are you
systematic offset.
okay? So are you talking about that? Are you talking about
No,
systematic
not
mismatch?
no. That is offset due to a difference between the biasing voltages of two stages. That's not
Hmm.
what. But there was a certain topic where um,
So
in
I
the
guess that the
just
thing that
yeah.
was that he was speaking was this one, right? That there is a MOSFET here, there is an R here.
That I understood, sir. Yeah, because of the mismatch between R and R, and yeah, between the resistors, there would be some common mode.
Correct. This is what he was
Yeah,
talking, right? Right now.
yeah.
So this, so the output here, this output, it will have a common mode and a differential mode, right? Component. So
It
that
would.
is
Yeah,
what he was talking about. But in the, if you have simple voltage follower like this,
yeah.
there is no significance of this common mode and differential mode, right? Because common mode and differential mode only come into picture when you have two signals, right? Here only you have only one signal here,
So
so
it
output will
comes into
always
picture
be,
only. Okay. Oh, so okay.
you have to have two signals, right? Two different signals to have common mode and differential mode, right?
Yeah. Okay. Yeah. Yes.
Right. So that is what it is. Okay.
Okay, so
So
if they are same, there is no chance for common mode, right?
no, there
If
is no
the
if
inputs,
there is only
no
one
chance.
common, if there is only one signal, then there is no common mode in this. And in this also, if CMRR is very high and this R1 R2 have no mismatch, then there is no chance of any common mode component at the output.
Okay, sir. So then one more thing. CMRR could be because of mismatch in the external resistors and also because of things which happen inside the op amp also, right?
No, no. Please mind it that uh, CMRR is not that. Okay, this is slightly different. Uh,
I mean, the common mode would of gain can be because of some mismatch of
yeah.
external resistors
Yes.
and because of
Yes. 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 Common mode gain can come here because in this is a particular special example. Okay, this is a very
okay,
special example of that special case basically, in which you see that the you get a common mode also because of the this thing, because of the mismatches in the resistor, you also get a common mode at the output. And this is a particular nuisance in certain cases where, as sir also spoke about it, The cases where you have a very large bias voltage, like 5 volt, 10 volt and all, okay, and the signal, the small signal riding on that is very small, which is like in let's say in millivolts or even lesser, in tens of millivolt, in hundreds of microvolts or so. In those conditions, this thing becomes very messy, because if you have common mode gain, a very small gain also can lead to a very large problem, because it will start affecting your overall response, isn't it?
Yeah, yeah. So,
Yeah.
so in this case, for R1, R2, and R1, R2, if they are perfectly matched, there's
Mhm.
only difference mode gain, right? Difference mode output,
Yeah.
right?
Yes.
There is
If
no
there is
problem
no common mode gain, if even if there is no if the CMRR of this op amp is also infinity in that case.
in that case. Okay, 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 sir.
Yeah. So what sir, the thing that sir talked about was that even when the CMRR of this particular op amp, let's say if it is infinity, but even then, if the two resistances are not matched here, okay, sorry, the resistance
Then there
matching is
will be
not,
CMR,
resistance matching is between these two. Okay, R1 here and R2 here. If they are not matched, then there will be a common mode
common mode
component
gain. Okay,
also,
okay,
which
common.
is not supposed to be there.
Okay.
Okay, now, so anything else?
Sir,
Yeah. Yes. Okay. So if there is nothing else, then thank you guys for joining. This was the last class. So all the best
sir,
for
I
your.
have one doubt. Sorry.
Okay. Okay. Yeah.
Yeah,
Go on.
sir. Last time also I asked about that common mode gain at high frequency, and you said you watched the lectures in week 12 of Nagendra sir. So I watched it, but I didn't seem to find anything like which would help me.
What did you ask?
Sir, one second. I'll just tell the exact question.
Uh-huh.
It's week 10. Week 10 question number uh, 5. Week 10 question number 5. That is find the low frequency uh, from yeah, low frequency. Sorry, high frequency gain common mode rejection ratio at 100 kilo.
Week 10, question number 5.
Yes,
Determine the common mode gain of the op amp figure 1 at 100 kilohertz.
yes.
Right. Okay.
So
So
you
for
said that
this,
in one of your previous lectures you described the method. So I understood the method, like you make the V in CM equal to, and then you make one of the inputs as V in CM and another is 100, and then you see the resistance of the output. But sir, I was not actually able to do it.
uh, hello.
Solve it.
Okay. So what I was saying that, so this part is actually covered in one of the lectures Nagendra sir talked about. So this is what he told that. Okay. So let me put it here.
Actually, sir, we have to find the effective tail resistance on that frequency.
Yeah. Yeah. Right.
That's
Right.
it.
Right. That is what you have to do. But let's say, let me cover it once. So you have this particular op amp here. You have this R. Okay. And you have this capacitor C, whatever, and you have this op amp here. Okay, you have this two which you have to connect to VCM, right?
Yes.
And this is like this, correct? Now tell me, can you use this common mode? Can you use half circuit concept here?
Mm,
Huh?
no,
Why? Why not?
sir, it's not exactly symmetric about the current source or some other
Correct,
point.
correct. So that makes the system not symmetric, right? The system is not symmetric, so you cannot use half circuit concept here, right?
Yes.
Half circuit equivalent. But now, if you do not use the half circuit equivalent, even then you can solve the circuit, right? You have to simply assume VCM here, right? And since you are have to calculate the output V out by VCM at what frequency? 100
100.
kilohertz. So you have to assume this capacitor also being there, okay? At 100 kilo hertz, the impedance of capacitor will be what? 1 over
It's
j omega
1
c.
over 100. Yeah.
Correct? And omega will be what? 2 pi into
Into
100 kilo. Right? So this is what will be the value of omega. Okay?
yes,
Fine. Now when you do that and when you calculate the V out over VCM, you will find the values. Okay. Now what Nagendra sir did is that you cannot use the half circuit concept here. So that makes the analysis slightly difficult, right? So what he did was that he said that you can still use the half circuit concept here if you do a small tweaking here. And what you can do is that you observe, you make a small observation here. What will be that small observation? When you use the same input here, VCM and VCM here, the input is same here, right? These two inputs are same, okay? And this is common for both the MOSFETs, right?
yes,
Right now. So VGS here and VGS here will be same, correct?
yes.
So can there be a difference between these two voltages? This voltage and this voltage?
Sir, if it is balanced, then it should not be a difference.
No, no, not balanced. I'm saying that the voltages are same here. The input voltages are same here.
Yes,
So what should happen to these two voltages?
they should be same.
Exactly, right? They should be
Yes,
same. So if the voltages are same, I can as well connect it like this, right?
yes,
Correct?
yes,
Now, but when I do this, now can you see that there is a symmetry here?
yes. Now that is
Right now.
yes,
Now you can use the half circuit concept, isn't it? Right?
yes.
So what will it be? It will be MOSFET here, correct?
Yes,
Or let's do this. Which will be diode connected, isn't it?
yes,
Then there will be MOSFET here, which will be VCM. Then there will be R, which will be 2R. Okay. C, which will be C by 2, and the current source, which will be what? Since it is a since we are talking about the equivalent incremental equivalent, we can get rid of this. Okay. So this will be the condition, and you will have to find out V out here, and you have to find V out by VCM. So now you can find it, right?
sir, but why did we ignore the current source over here?
Okay, so I assume that the current source has infinite resistance. That is why I ignored
Okay,
it.
okay,
If it does not have infinite resistance, you'll have to assume some output resistance of current source, and then you'll have to only put the the output resistance of the current source, and the current source will be again gone.
okay.
Fine. So now you can do this, right?
Yes,
Okay.
So the answer that we get from this procedure would be the same if we consider the first one as symmetric, right?
What first one is symmetric?
Like if the differential pair with the current mirror, if we consider that if the resistances, if we consider that as symmetric, and if we proceed with the common mode half circuit,
Uh-huh.
um,
Okay, so let's
would we,
let's let's do this again once again. So you are saying that now you have to consider, we can consider symmetric. You are saying
yeah, would we get the same result as,
you will not get the same result because now it is not symmetric, right? So how will you tell me what will you do for this upper part? How will you split it into two equal halves? One part will be diode connected, one part will not be diode connected, isn't
directly?
it?
Yeah.
So how will you do it in that case? Here we did this because both the parts were diode connected, isn't it?
Okay. Okay.
Correct.
Okay. Yeah.
So that you took one half only and diode connected it. You cannot do the same here, right? You have to have that connection here to make it symmetric.
Okay. So, okay.
Yeah.
Sir,
Yeah.
sir, one problem I faced during this assignment problem, like
Mm-hmm.
you said that we can find the capacitive impedances due to the capacitance at 100 kilohertz frequency.
Uh-huh.
with the parallel with this the tail resistance.
Mm-hmm.
So we can find the overall tail resistance of the circuit.
Uh-huh.
So calculating this way, we are getting some value,
Mm-hmm.
and while we doing like R parallel C, like R by 1 plus SCR thing, and
Uh-huh.
putting like calculating the mod value of this effective resistance at 100 kilohertz,
Mm-hmm.
then the two effective resistance I am getting is like slightly different, like
No, it should not be
5% or
different.
10%.
No, no, it should not be different. You are doing something else. You are doing a
Okay,
calculation, some calculation mistake. It should not be different.
okay, okay. I will check, sir. Yes.
Yeah, yeah,
If I,
yeah, yes. Okay, so I guess the time is also up. Okay, so let's leave it for. I mean, let's end it today. And thank you all for joining. And this is the last. This was the last session. So I guess you enjoyed the sessions. Whoever was at least joining the session, so they enjoyed it at least. I hope so. And you learned something from here. And so thank you everyone for joining. So this was also a learning experience for me. Fine. So oh yeah, by the way, all the best for your exams. So I hope that you
Thank you, sir.
do well in your exams and
Thank you,
get an
sir.
interview lined up with the with TI. Okay. I hope so. I I congratulate you. Sorry, I hope for your better future. Okay, in this particular field. So thank you all. Thanks for
Thank you, sir.
joining. Thanks for listening to me.
thank you, sir.
Thank
Thank
you.
you.
Yeah. All the best.